Pose with the fans. Pose with the pose with the pose with the fans. Pose with the.
Hello everyone! Welcome to this chemistry learning video. Today, we'll explore an important topic in organic chemistry, that is the molecular model of cis-trans geometric isomers in alkenes. And then my best friend, the Gian Devina, will be continue the presentation with the material that is the molecular model of easy geometric isomers in alkenes. So let's get started. The first is, what are geometric isomers? Geometric isomers are isomers that have the same molecular formula and the same bond arrangement, but differ in the spatial position of atoms or groups around the double bond. This occurs due to the rotational limitation on the double bond P in alkenes. Cis-trans geometric isomerism in alkenes occurs due to the rotational constraints on the double bond. In general, only alkenes that have two different stupid twin on each sp to the power of 2 carbon can form geometric isomer. The second, why do geometric isomers form? So alkenes contain double bonds made of one sigma and one pi bond. The pi bond prevents rotation, so if each carbon of the double bond is bonded to two different groups, the molecule can exist in two forms. The first form is cis, when similar groups are on the same side, but the second forms is trans when similar groups are on opposite sides. However, if one of the double bonded carbons has two identical groups, geometric isomerism cannot occur. So let's explore some clear and simple examples of cis-trans geometric isomers in alkenes. This will help you visualize how the position of atoms around a double bond can affect the shape and properties of a molecule. The first example is 2-butene. In cis-2-butene, the two methyl groups are located on the same side on the double bond. Like imagine two people sitting next to each other on a bench. That's the cis form. And in trans-2-butene, the methyl groups are on opposite side of the double bond. It's like two people sitting on opposite ends of a seesaw. That's the trans form. Even though the chemical formula is the same, the spatial arrangement is different, which can lead to different physical properties such as boiling point and reactivity. The second example is 1,2-dichloroethene. In case 1,2-dichloroethene, both chlorine atoms are on the same side of the double bond. This creates a bent or V-shaped molecule. But in the trans form, the chlorine atoms are on opposite side, making the molecule more linear and symmetrical. Because of this difference, cis and trans isomers of dichloroethene have different dipole moment and boiling points. The third example is trihexane. Let's look at a longer carbon chain. In cis-trihexane, the two carbon chains branching from the double bond are on the same side, causing the molecule to bend slightly. Meanwhile, in trans-trihexane, the chains are on opposite sides, creating a more straight and stretched structure. This subtle change can influence how the molecule behaves in reaction or fits into biological system. The fourth example is 2-pentane. In this example, in this case form, the two main carbon groups are on the same side, giving the molecule a cubed shape. Meanwhile, in the trans form, they are on opposite side, making the molecule more symmetrical and usually less polar. The fifth example is butanedioic acid. This is a special case of cis-trans isomerism in molecules with carboxylic acid group. The first is cis or maleic acid is the cis isomer with both carboxylic acid groups on the same side of the double bond. Because the acidic groups are close, maleic acid can form internal hydrogen bonds which affect its reactivity. Meanwhile, in trans or formic acid is the trans isomer with the carboxylic acid group are opposite side, making it more stable and less reactive in certain conditions. The sixth example is 1,2-dibromoethane. In case 1,2-dibromoethane, both bromine atoms are on the same side of the double bond, making the molecule polar. Meanwhile, in the trans isomer, the bromines are on opposite side, which make the molecule nonpolar, even though both have the same atoms. This difference in polarity influences how the substance dissolves in water or interacts with other molecules. And the last example is 1,2-diodoethane. In this final example, the iodine atoms are the K groups. Just like before, the Cs form has both iodine atoms on the same side, while the trans form has them on opposite side. Even though the difference seems small, it can change how the molecule behaves physically, including its melting point, boiling point, and crystal structure, even though the reactivity. So I think that's all from me about the material, and the presentation will be continued by Gian Devina. Thank you, guys.
We're going to talk about an important topic in organic chemistry, ENZ geometric isomerism in alkenes. This topic is crucial for understanding molecular structure and how the properties of compounds can differ significantly even when they share the same molecular formula. Before the ENZ system was developed, we used the terms cis and trans to distinguish geometric isomers in alkenes. However, this system has limitations. It only works when each carbon in the double bond has two identical substituents. But what if all four substituents are different? This is where the ENZ systems comes in. It is more systematic and can be applied to all types of alkenes, no matter how complex their substituents are. So, the determination of E or G configuration is based on the Chan-Ingold-Prelog priority rules. We compare the substituents attached to each carbon in the double bond. The substituent with the higher atomic number gets higher priority. In the case of double or triple bonds, we treat the bonded atom as if it's connected to phantom atoms, and the total weight determines its priority. After assigning priority to each pair of substituents, we can determine the geometric configuration of the alkene. If the two high priority groups are on the same side of the double bond, the configuration is G, from the German word zusammen, meaning together, and if they are on opposite sides, the configuration is E, from the German word entgegen, meaning opposite.
네 분위기에 완벽해 두근거림은 멈추지 않아 매일 더해 네가 그리 손에 어두워져도 it's okay 어둠도 밝게 느껴지는 이유 그건 it's you 막을 생각 없어 계속해서 널 찾고 있는 건 나야 한시도 떨어질 수 없어 계속해서 널 곁에 두고 싶어
Application of the EZ systems in organic chemistry. Why is this system important? Because ENZ configuration can affect melting point, boiling point, and even biological activity. For instance, in pharmaceuticals, ENZ isomers may have completely different therapeutic effects. That's why understanding and applying the ENZ system is essential in the synthesis and analysis of modern organic compounds. Okay, that wraps up our discussion on ENZ geometric isomerism in alkenes. I hope this explanation helps you grasp the importance of the system in chemistry. Don't forget to practice the determining E or G configuration for various compounds. See you in the next learning video.